Wait, you screwed up our photo op. No, come here, come here. We have a tradition of taking selfies around the world together. So we
need a camera.
I have a photographer placed strategically out there in the crowd.
Beautiful.
All right, thank you very much. So you just stole my punchline. Thank you very much. About machines and kids. This is Andrew Ng, and he's representative of someone who I think thinks that AI is more or less around the corner. I have a quote up here. Well, I'll show you the exact quote later, from Andrew Ng that was in Harvard Business Review. He said, basically, if a person can do something in a second, a machine can do it too, either now or in the near future. And I think this is typical of the optimism about AI that we see. Andrew, as you may know, was head of AI research at Baidu until recently. I think he's half right. There are some things that people can do in less than a half a second that AI is actually pretty good at. So you can train a deep learning neural network to recognize that this picture is Tiger Woods and that it is not a golf ball. You can probably also get it to distinguish from Angelina Jolie. Basically, the idea is you have big data in, statistical approximations out, and by now, probably most people in an audience like this at least have seen a convolutional network or heard of a neural network before, a deep learning system. That's the kind of standard tool that people are using right now in artificial intelligence to solve almost every problem that they go after. It may or may not succeed in this, and I don't know if it's too soon, but you can see whether your image recognition device can recognize that this is also Tiger Woods. I won't count against your AI system if it can't. But perception is more than just identifying objects. So there's a lot of excitement about AI systems recognizing objects nowadays, but even in the domain of perception, we have to do more than just recognize the objects. We want to recognize the relations. So a deep learning system might actually struggle to recognize that there is a dog in this picture because the ears are in an unusual orientation because the dog is sitting down. No deep learning system could tell you that this is really bizarre, that it is very unusual for dogs to be doing bench presses, right? You might sit there and wonder, like, how did the dog get to be so ripped that it could have managed to do this, and so forth. If you are a human cognitive system. If you're a deep learning system, you just say dog and barbell, and that's the end of it. You don't have any real understanding. If you're human, you can look at this and you can tell why it's funny or tragic, depending on your point of view or how morbid you are, right? Here's somebody who's jumped out of an airplane and they say, oh shit, this isn't a parachute, it's just a backpack and a fanny pack. Well, a true intelligent system should be able to look at a scene and be able to predict what's going to happen next. It's not, it's grim in this case, but you can all do it without too much trouble, because perception is more than just identifying the objects. It's about understanding what happens in a scene, what's happening in the world. I would say that AI is actually not very good at this. Of course, if you read the newspaper, you wouldn't believe me. So this was on the front page of the Times, in the study that came out of Google. There was a new database, and people trained systems to do captioning. So a group of young people playing a game of Frisbee, you could say that in a second, and so can this system from Google. It could identify in a second what's going on. And the Google system could also do this one, a person riding a motorcycle on a dirt road. Now I'm going to give you the next one. I'm going to see if you can identify what's going on, because we're testing the conjecture that human beings can do various things in 1 second and machines can too. So what is this one? Well, you can, it's a little bit tricky, but you might tell me that it's a parking sign with stickers on it. If you were this particular Google system that was on the front page of the Times, you would say it's a refrigerator filled with lots of food and drinks. Those of you who know Oliver Sacks' most famous book will recognize this as an homage to that book, which is The Man Who Mistook His Wife for a Hat. Of course, the man who mistook his wife for a hat notably had brain damage, right? And I think if you think about the deep learning systems carefully, they're actually a little bit like humans with brain damage. What's this? Anybody know? You probably say like it's a pattern of stripes or something like that. If you're a deep learning system, you think it's a school bus. How about this? What do you think? I don't know. You probably have no idea what it is. If you're a deep learning system, you're pretty sure it's a digital clock. If you are a defender of deep learning system, you will say that it's an optical illusion. And, humans are subject to optical illusions. I would say these are more like hallucinations. They show what's commonly the case in deep learning, which is if you move away from the training set, move away from the cases and supervised learning, you got inputs and outputs paired together. As you move away from those, the systems start to produce bizarre answers often. So here's Andrew Ng's actual quote. If a typical person can do a mental task with less than 1 second of thought, we can probably automate it using AI either now or in the near future. Now I want to give you an honest rendition, a realistic rendition of that. If a typical person can do a mental task with less than 1 second of thought, and we can gather an enormous amount of directly relevant data, we have a fighting chance, so long as the test data aren't too terribly different from the training data and the domain doesn't change too much over time. This is where AI really is. It's not nearly as optimistic a place. It says that there are going to be lots of problems we can't actually solve with current technology. So there's a problem that fits in really well with what's there on the right, and that problem is playing Go. Right? You can get an enormous amount of data. The rules are stable over time. The data are directly relevant. And so AlphaGo is pretty good at that. But if you look at the same kind of algorithms in a context where things change, they're not nearly so good. So you can spoof these systems in much the same way as I showed with the yellow and black stripes. So you can add a few pixels to the famous Atari game system from DeepMind, and the whole thing falls apart. It can't play anymore because it doesn't have abstract ideas like barricade or shooting or any of that kind of stuff. So we're actually a long way away, I think, realistically, from having AI systems that can do anything a person can do in a second. They can do some of the things a person can do in a second, but most of them they can't. And that means a lot of what we might want to do remains out of reach. So some things AI has actually done really well lately, and problems that for a long time seemed pretty intractable. So speech recognition is a much easier, or much more feasible, I should say, problem than it used to be. So we can now do speech recognition, at least in quiet rooms with white males asking search queries. As you move away from that, as you move to the boundary cases, it becomes harder and harder. So somebody with an accent, somebody in a noisy room, maybe they're not asking a search query, doesn't work as well anymore. Image recognition works in bounded worlds. So if you only see school buses and digital clocks, you might be good to go. The problem is maybe you see something that isn't a school bus or a digital clock. It's not in your training set. Your system doesn't work. Natural language understanding works in narrow bounded domains. So you can ask your Amazon Echo to play any song in your collection. Great. But here's a question you can't ask any system today. How much did transistors cost when the Macintosh Plus was released? The data are there on the web. You could look up the individual components and you can put them together. But there's no search engine that will do that for you. So you can do some of these things, and of course we're very good at advertisement targeting. But there are lots of things we can't really build yet. So we don't really have conversational interfaces. We don't have automated scientific discovery. We don't have automated medical diagnosis. We don't have automated scene comprehension as opposed to just labeling the things in a room. We don't have domestic robots that work. And we don't have safe and reliable driverless cars. So we still have a long way to go. The way I think of it is perception is just one of the many human cognitive abilities, like common sense, planning, analogy, and so forth. All the work that's happening right now is really on perception. So we're making real progress on perception, but most of the rest of AI, I think, is getting left behind. My biggest fear about AI is not the Terminator. My biggest fear about AI is that we're going to get stuck, that we're going to get stuck in a local minimum. We're trying to reduce the amount of error on any given problem, and we're sort of doing that on a field-wide basis, but we might be getting stuck in a local minimum. We're not getting to the bottom of the mountain range we really need to get to. And if AI never progressed, that would be a shame. So if all we could ever do was target advertisements and prioritize search queries, I think that would be a disappointing outcome for AI. We'd like to have machines that can read, that can cure cancer, that can help us with biology and all kinds of ways to understand how the brain works for domestic robots, et cetera. But what we're doing is gradient descent through model space. So gradient descent is the technique that people use in order to do these things like object perception. And we can see that in the field itself. We get a little bit better each year at things like object perception. But there are other domains like natural language understanding where it's not clear that we're actually, by taking little small steps rolling down a hill, that we're actually getting where we need to go. The fundamental risk is that we might spend tons of researcher time only to get stuck, reach an asymptote. And that might be fine in certain domains. So if you build a recommendation engine and it recommends 7 songs you like and you don't like the 8th song, so what? You're not even paying for the songs anymore. It's not too much of a tragedy. But if you build a pedestrian detector that's 97% correct, that means 3% of the time you have a serious problem, right? Same thing if you have a domestic robot interacting with live humans. If it lifts up your grandfather 9 times out of 10 and puts him in the bed correctly, that's great, but the 10th time, that happens a few times, your company's out of business. So why aren't we there yet? Why haven't we gotten to strong AI? One problem is that engineering machine learning techniques is a lot harder than engineering with classical techniques, although there are problems in both cases. Peter Norvig gave a great talk at another EmTech in San Francisco about a year and a half ago, talking about how these systems are difficult to debug, it's hard to revise them incrementally, and they're difficult to verify. We don't know how to verify machine learning solutions. He had a great line, which is like, your system works on Tuesdays and Thursdays, but maybe it doesn't work on the holidays, and you're not really sure why, and you just don't have techniques to deal with it. So we have no procedures for reliably building complex cognitive systems. I just saw this cartoon by XKCD that I think really captures the field. Someone says, this is your machine learning system? Yep. You just pour the data into this big pile of linear algebra and then collect the answers on the other side. And somebody said, but what if the answers are wrong? And you say, well, you just stir the pile until they start looking right. So that is the methodology here. You stir the pile of linear algebra till the solution looks right, and maybe that works on the holidays and maybe it doesn't. There's a great paper by John Scully's nephew, who's at Google, D. Scully, called Machine Learning, the High-Interest Credit Card of Technical Debt. And the point is, you make these solutions, they seem to work, but they're not necessarily robust, and you wind up building more and more promises that don't get you where you want to go. I wrote a paper for the ACM, Communications of the ACM, with Ernie Davis on common sense reasoning. And in some ways, the best thing was the cover, which I did not have anything to do with, but it really captured the point of the story. So you have a robot there with a chainsaw cutting down a tree limb. But the robot is on the wrong side of the tree limb. And so you can use your human common sense reasoning to realize the robot's going to fall. Anyone underneath is, in deep jeopardy. Well, you can't do this with a paradigm of supervised learning. So you have 50,000 trials of robots and tree limbs falling and occasionally killing people. That's just not going to work. The problem is we're equating statistics and knowledge, and in many cases, you can't get the knowledge you need by having large sample sizes. The third problem is that the standard bias in the field is to assume basically everything's learned. People in the field just don't want to build anything in. I think it's just a sociological preference and not coming from anything that we know about developmental biology, developmental neuroscience, evolutionary biology, any field like that. If you actually look at biology, there's lots of stuff built into our genomes. Our genome gives us a program that builds a rough draft of our brain. Half our genome, more or less, is involved in constructing the brain. But then you have people like Jan LeCun, who's a major figure in the field. He invented the convolutional net I showed you before. And he's like, well, what we want to do is we want to get machines to understand video. You just show it a few frames of video and it predicts what's going next. LeCun's paradigm is you're just going to learn everything you need to do by watching enough videos. I don't believe it's ever going to happen that way. And part of the reason I don't believe that is because I've studied cognitive development all my life, language acquisition in human children. I'm always trying to persuade people that humans are born with interesting innate endowment. And Steve Pinker, my mentor, made that argument. Noam Chomsky made that argument. Liz Spelke made a really great version of that argument. Nobody ever believes it with human beings. So instead of wasting your time trying to persuade you that humans are born with innate structure, I will instead show you a baby ibex. And this baby ibex is going to climbing mountains. It's like a week old or a month old. And you just can't watch this and think there's not some innate structure allowing it to clamber down this hill and not fall over. It must know something innately about topography, about climbing, about what's safe, what's not. It scrambles, but it doesn't fall. Like, this is amazing. And this is, zero trial learning, right? If you screw up once, your genes don't go in the gene pool. Right? So evolution has shaped these creatures to do phenomenal work innately. Now, in the interest of fairness, I compare with robots. Probably a lot of you have seen this video before, but so I won't belabor it. But this is, robots from the DARPA competition, right? They're not at the same level as the ibex, and I think it's partly because they don't have the same innate knowledge. All right, how can we move forward? I think there's a couple things we can do. One is I think we need collaboration here on a grand scale, and it can't just be all done in Google. So most AI research now is done in Google. It's in the larger framework of trying to sell advertisements. Maybe if we want to get to things like automated scientific reasoning, we need interdisciplinary collaboration between lots of people, lots of countries on a scale we just haven't tried it in order to take on hard problems. The other thing is I think we should look at human children. These are mine. Chloe is on your left. Alexander is on the right. Here they're doing some stuff with modeling clay. And I'll just give you one example from their considerable cognitive powers. So Chloe made an artwork a few months ago when she was not quite 3 years old. And I said, why don't we put it in Mama's armoire? And she responded by saying, well, that way Mama doesn't see it. But when she opens it, the armoire, she can see it. So she's 2 years and 10 months old. And this shows us a bunch of things. So she was able to infer the intent behind my proposed plan. she was able to articulate the reasoning behind the intent. So we look at these deep learning systems, nobody knows what's going on. She was able to reverse engineer my learning system without even doing a brain scan, figure out what I was trying to do. We don't have AI systems that at this point understand people's intent. We don't have AI systems that can predict a potential future without directly observing it, right? So she had never seen this before, but she'd seen how the armoire worked. She was able to put it all together. In fairness, I asked Siri the same question. What happens when you put an artwork in the armoire? And Siri, as usual, chickened out and passed it along to Bing because it had no idea. And Bing said, as an answer, it just referred me to a website which said, what happens if you break an artwork? Well, that's a totally different question and kind of the state of the art. So I will end with a rhetorical question, which is, isn't it time we learn more from human beings for how they do cognition instead of just doing all this bottom-up perceptual learning that is so popular in the field right now? Thank you very much.